Now recall from our previous video, we want to realize some circuit that could produce this function phi of t, which has a Fourier series that results in these increasing cosines, all of which are some factor or multiple of our carrier frequency. So we want to come up with some circuit that has cosine waves, each one being at a progressively higher multiple of our carrier frequency. So Fc times 0, Fc times 1, Fc times 2. We want to make a circuit that has this type of Fourier series. So to do that, let's consider the periodic pulse. So you could imagine this as a switch turning off and on repeatedly. The pulse, when it's on, has a width of pi, and then it is off again for another width of pi. It starts at minus pi, goes up to pi, and when it's on, it goes on, and then it turns off. So it's on, then off, on, then off. Now, the compact Fourier series can be written like this, where you have one first coefficient for n equals 0, then an infinite sum of coefficients from n equals 1 all the way to n equals infinity. And so if you look in chapter 2, this is how you will see them describe the compact Fourier series. And the compact Fourier series has this system where the C0 is equal to A naught, whereas Cn is equal to A sub n squared plus B sub n squared, and then the phase is the inverse tangent of B sub n over A sub n. So now what are A sub n, B sub n? What are these coefficients? Let's consider this, and let's see if we can derive the coefficients for this periodic pulse. So before we go any further, let's take a note that the frequency of this, the radial frequency, must be equal to 1. So the frequency we could say is 2 pi f naught or omega naught, and omega naught is equal to 1. Therefore, the frequency must be 1 over 2 pi with a period of 2 pi from minus pi to pi. That's what the period is. And we're going to be using this information as we go through this work of finding the coefficients. So each of these equations, each of these integrals describes how to find the coefficients. So that A naught has this integral from the t naught half to minus t naught half to t naught half. And then the A sub n is a cosine integral, and the B sub n is a sine integral. Each of these can be simplified a bit so that we integrate instead of going from half of the period to a quarter of the period. And that's due to this switching nature where we only have something to integrate right from here to here. So we're able to simplify this a bit. So we have 3, right? We have 1, 2, 3 integrals that we're going to need to do. Let's start with this one. So the A naught, and we'll say that this, right, we can see that our value of Wt is 1. So when it's on, we're at 1. When it's off, we're at 0. So we're going to substitute with 1. And then we're going to, instead of integrating from the period minus half a period to half a period, we're going to integrate from minus a quarter period to quarter period. Now that equates to minus pi half to pi half, right? And that's because, right, our quarter period, minus quarter period to quarter period is minus pi half to pi half. And that's because if we look all the way back here, right, our full period is 2 pi. Now, if we do that, we can substitute then 2 pi for the period. And now we have this full integral of 1 from minus pi half to pi half multiplied by 1 over 2 pi. Completing that gives us this for our first coefficient. In the next videos, we're going to find the coefficient A sub n and B sub n.